Thanks, Oscar. Hopefully what he said about me was nice. I didn't understand most of it. But so yeah, I'm going to talk about emissions in chemistry of air pollution in London and Beijing. I've called it A Tale of Two Cities. I don't know how much that reference means to people here. It's a famous book by Charles Dickens. It has nothing to do with air pollution or atmospheric science. It's just the title fits quite nicely. The book is set in London and Paris. My two cities that I'm going to mainly talk about are pollution in London and Beijing. As Oscar said, I'm from the University of York in the UK. I'm also part of the National Centre for Atmospheric Science. I just thought I'd put a few pictures up to show where I'm from. I don't know how many people here have ever been to the UK or to York in particular. Some nice photos. It's an old, originally Roman city with still a Roman wall still existing and a very spectacular medieval minster or cathedral. There's a picture of the university from above. It's nothing like the size of your university here. There's about 15,000 students, something like that. But this is the campus. It's out to the east of the city. I'm from the chemistry department. You can see this photo was actually taken. This is not Photoshop. This is a picture of our research aircraft, the UK's research aircraft, when we did some work looking at pollution from York. I'm not actually going to talk much about the aircraft today, but I thought that was quite a nice photo to put up. But more specifically, I'm from the Wolfson Atmospheric Chemistry Laboratories, which is a part of the chemistry department, but we got some money a few years ago to bring all the atmospheric chemistry research and atmospheric science research into one building. I'll not say too much about it because I think Oscar introduced it, but there's around about 50 researchers in 7 different academic groups. And we do research into air pollution, stratospheric ozone depletion and climate change, so all the facets of atmospheric science or atmospheric composition anyway. I'm obviously going to be talking mainly about air pollution today. So here are my two cities, London and Beijing. Just as a brief introduction, and most people will already know this, urban populations have risen from 3% of people living in cities in the 1800s to around about an estimated 47% by the end of this century. And along with that has come issues surrounding air pollution, which is obviously a significant factor in global health. There's numerous studies out to show that air pollution kills millions each year. In the UK, it's a major problem. It's in the public consciousness. It's always in our newspapers. Various quality and political-leaning newspapers always report on air pollution. If there's a high air pollution episode, it appears on the weather forecast. But we have some key policy questions in the UK that I've divided into 3 of them. Basically, why isn't NO2 going down anymore? Why isn't particulate matter improving very much beyond the roadside? And what's the future of ozone? And from a UK point of view, the first part of the talk, I'm going to concentrate on this question of NO2. So this is a plot of NOx in London. So this is the UK's atmospheric emission inventory from the start of the 2000s up to 2016. You can see this, what should a significant decrease in the estimated amount of NOx emitted from, this is just the vehicle emissions, so road transport emissions. But in London, London's a very well instrumented and monitored city for air pollution. This is just a few of the monitoring stations. There are about 150 of them in total. With the next plot I'm going to show just shows data from these. And this shows the actual concentrations of NOx as measured on the roadside and in an urban background site, so a site similar to where we're at now. And you can see up to the mid-2000s, there'd been a significant decline. But from over the last 10 or 12 years, essentially NOx, particularly at the roadside, hasn't changed. And in some, you might argue that it's even started to increase. This is despite the estimation that NOx should have decreased. The emissions of NOx, at least from traffic, should have decreased significantly. So one of the questions we wanted to answer is what's going on here? Why is that the case? So yeah, 20% reduction in concentration since 2002, but a 60% projected reduction in emission. So we did a project about 3 or 4 years ago now called Clean Air for London. It was a wide-ranging project, and it had measurement sites at a rural station and in an urban background, North Kensington. It's a picture of a load of the sea containers containing equipment at this site, which is actually a school, a primary school in North Kensington. Had some measurements at Curbside, the Marylebone Road site in central London, and then rural sites kind of to the east of London, so to catch the downwind. But what I'm going to talk about is the measurements we made at elevated sites at the BT Tower, which we were very lucky to have access to. The project involved a load of core measurements, long-term, but also these intensive operation period where we made a huge range of gas and aerosol phase species. And I'm going to basically just talk about the long-term measurements at the elevated site today. So here's the BT Tower in London. You can see it stands out. It's in the sort of west end of London, and it stands out as the tallest building for a large distance around it. It was built in the 60s as a communication tower, and we're lucky enough to get access to the 35th floor, where we've got a site to put some instruments, and we ran a sample line all the way up to the top, which is about 190 metres above the street below. What we did there was make fast 10 Hertz measurements of NO and NO2 using a chemiluminescence system, and I'll just so if you see where the BT Tower is in London, it's here, so central London, measurement height of 100 metres. We think of the footprint of the site, so where the air comes from that we measure, stretches to around about 3 kilometres or maybe a bit more, so this kind of distance. So we're measuring air that's basically relevant to central London. The next tallest building, about 130 metres, and the average canopy height around it, and this plot, the green colours here are sort of shorter buildings, the red are taller buildings. Essentially around it is pretty low height, or reasonably low height buildings at 50 metres or less. So yeah, coming back to the instrument, we put a NOx instrument up there, chemiluminescence, but using a blue light converter to convert NO2 to NO, and therefore we were able to measure both NO and NO2 at 5 Hertz. There's our little NOx mascot that travels wherever the instrument goes to. In theory, it brings us luck. What we were then able to do is because we were able to measure at 5 Hertz, we were able to use this to calculate fluxes using the eddy covariance technique. Now, I'm not going to go into this in any details, but essentially it's the deviations of vertical wind speed and the deviations of concentration gives us a flux. And we got around 60 days of flux measurements in summer 2012 and spring 2013. The idea was to measure for around about 2 years. We had all sorts of instrument problems, but we still got 60 days of measurements, and to our knowledge, these were the first measurements of NOx flux in a large city like London. This is now the BT Tower's footprint. You see these circles here are the approximate distance of the footprint, and these are put onto the atmospheric emission inventory for London. And for those of you that know London, that you can see around here, that's the outer motorway or highway around the outside of London. The big red blob there is Heathrow Airport. So that stands out really clearly as a massive emitter of NOx. So the hotter colours here are higher NOx emissions, the colder colours are lower. But you can see in central London here, apart from Heathrow Airport, it's the highest areas emissions of NOx. And that's what we were able to capture using the data from the BT Tower. So what did that show? And we published this a couple of years ago. Essentially, on this graph here, this is the sort of average footprint radius from the tower up to some days where we got 20 kilometres, and the black trace here shows our measurements of NOx emissions in tonnes per kilometre squared per year, and the red bars show what the atmospheric emission inventory estimates, and you can see this significant sort of 40% discrepancy between what's estimated to be emitted and what we've directly measured to be emitted using eddy covariance technique. So we've made no sort of thoughts as to why this is. There are various reasons, but what we wanted to do then is to assess, well, how relevant is central London to the rest of London? How can we assess that? And obviously we can't move the tower. There are not really any other suitable sites in London. So what we were able to do was we got some money to actually put this eddy covariance technique on board an aircraft. And you can see, this is a picture taken out of the aircraft. It was a Dornier 228, so a similar size to a sort of Twin Otter or a King Air. We were able to make these measurements. We also measured VOCs as well. I'm not going to talk about those. I'm just going to talk about the NOx. And we were able to fly essentially legs at about 300 metres above the ground across central London. And here's a picture of our flight legs. This is central London here. Essentially from the southwest to the northeast, we just continually repeated these legs. This is coloured by NOx concentrations, actually. You see we pick up the higher NOx from central London. That's Heathrow Airport there for the just for the scale. And then we converted that data to eddy covariance using a continuous wavelet transformation technique. Again, I'm not going to go into that in any detail, but that enables us, rather than the standard eddy covariance that gives you data point every half an hour, we were able to get a data point every sort of 10 seconds, so to really get that spatial resolution. And this is our flight track with the flux footprint on it that we calculated, and you can see as we go from the southwest to the northeast, we cover the bit of central London that the BT Tower measures, but also we get the bits of the suburbs of London as well. And that's what we really wanted to capture, to see how does the inventory do outside of central London. And these are the results. So just concentrate on this plot here. This is the measurements in the green as we fly from the southwest to the northeast. And the red here is the emission inventory, so the inventory underneath that footprint that we calculated. And you can see in the suburbs here, there's still a discrepancy, but it's a lot closer than the data from central London, which has a factor of 2 or 3 discrepancy between the inventory and the measurement. Interestingly, actually, in central London, this green bit here is domestic consumption or domestic burning. So actually in central London, non-vehicle emissions are more prevalent than they are in outer London. So that was one thing that was interesting, and maybe an error in the inventory. But what we did, we tried to enhance the inventory by using a real-world traffic emission data, putting in. So a group at King's College London have a very detailed emission inventory specific to London that's on a sort of 50 metres square rather than a kilometre square grid. And so it has much better traffic representation, including real-world traffic flows and, importantly, real-world NOx emissions. So the national inventory uses emissions that come from what the Euro standards are that should be coming out of exhaust, whereas this London emission inventory uses real-world measurements of NOx coming out of vehicles. And if you look at the difference, this is the national inventory at 1 kilometre grid square traffic NOx. And on the same scale, the London emission inventory, now this is the road traffic NOx. And you can see there's been a significant increase in the amount of NOx estimated if you go to this enhanced emission inventory. And then if we look at the results, what we get is that actually in outer London, the inventory and the measurements agree pretty well, but we've still got this significant discrepancy in central London. London's a very odd city actually for traffic, because inside central London there's virtually no or very small percentage of private vehicles. It's almost all buses, taxis, vans, trucks, delivery vehicles, because there's quite a large congestion charge. It's about $20 equivalent to drive in central London. So people don't. And while that's had an effect on the sort of traffic flow and everything, it's improved that in London, because all the buses, taxis, etc., at least at this time when we did these measurements a couple of years ago, are essentially diesel vehicles. We've still got this discrepancy between what's estimated to be emitted and what actually is emitted. So are these Euro controls not working? This is measurements that were made a few years ago now. I'll just talk you through this graph. The plot here shows the type approval emissions, so the different Euro standards, 1, 2, 3, 4, 5, 6, as we've moved on in time, of what should be emitted in terms of NOx. And then the red points here show real-world remote sensing data of what actually is being emitted. And you can see It's a significant discrepancy, and even for the latest vehicles, at least in 2015, the Euro 6 vehicles, they're still, although they've dropped, it's still way above what should be, what essentially comes out of the laboratory measurements or the rolling road measurements of vehicles. If you look at petrol, actually, the latest petrol vehicles in Europe and in the UK emit virtually no NOx. So this is why London is such a problem, and in the UK, because we've got a very large percentage of diesel vehicles. We've finished those measurements in 2013. We've actually recently started them again, so we've now got a much sort of improved instrument, and went back in 2017 and measured for 6 months. The instruments had to be taken away again because it got funded to go on a project in Delhi, in India. But anyway, we've got sort of 6 months worth of data, and you can see the sort of diurnal cycle here of different days of the week. Again, interestingly, in London, Saturday seems to be very similar to the rest of the week, and it's only Sunday where there's a reduction. But you can see, again, we've got this discrepancy between the inventory in the white and the measurements in the yellow, pretty similar to what we saw before. And this is the average across all of that time. So there's, again, about a factor of 2 difference still, even with the latest inventories and the latest measurements. And I just thought I'd plot this up for a bit of fun, just to show the difference in March and April 2013 to March and April 2017, the average diurnal of NOx flux. Actually, UK roadside NOx measurements have decreased by about 5% from 2013 to 2017. London does appear to be slightly different, but again, there's been very little reduction in NOx emissions or concentrations throughout the UK, but in the last 4 years. So we've still got this problem of NOx and obviously NO2 in London. One of the other things that we've done this year is to use our research aircraft, and this is it. It's a converted airliner. It's a BAE 146. It would seat about 100 people if it was a passenger jet, but basically most of the seats have been ripped out and replaced with instruments. And we've done some sampling around London, so essentially to look at the bulk emission from London and the southeast of England. So we did lots of legs up and down in the North Sea here, in a southwesterly conditions where the air was taking all the emissions from London out into the North Sea. We also did a flight. This is Manchester-Liverpool area, so we actually did a flight looking at the emissions from a different UK city, because we got a bit fed up with just continually looking at London. This is an example of the stacked legs, and you can see the colour. The hotter colours again show the increased NOx, so you can clearly see the London plume. And then we use a Kriging technique to fill in the data, and then a mass balance, so basically taking off what's coming in, off what's come out, to calculate a flux. This is very ongoing. I haven't got any results from this, but it's just to show what we have been doing. The key thing with this is, where has that air come from? So we've used some high split dispersion models along our flight track to sort of cover, or to try and estimate what we're measuring, exactly where it's come from, and then we'll transpose that onto the emission inventory and be able to get a comparison of the emission inventory compared to the measurements for the entire area of the southeast of England, using a different technique to the fluxes. And like I say, this is ongoing work, so I haven't really got any results from this at the moment. And we've started doing the real-world exhaust emission measurements again. So this is the system with the laser beam here and the detector across the other side of the road. Actually, the laser beam there, the detector here. And as the vehicles drive through here, it measures what's in their exhaust, takes a photo of their number plate so we can link back to what type of vehicle it was. This was set up in York in 2017. Last year, early this year, we took it to London, and we've got samples of about 30,000 vehicles that we're currently working through. And you can see here some early results. This is a similar plot before. These are the different Euro standards in the different blocks, 3, 4, 5, 6. And even the very latest Euro 6 vehicles, 2017 manufacturer vehicles, still this significant discrepancy between what the Euro standard says and what our measured emissions are. So just to conclude on London, we measured this NOx flux from town aircrafts, potentially significantly higher values than emission inventories. If you use a better vehicle emission screen, it helps out, especially in outer London. and the real-world tailpipe emissions are much higher than standard still, even for the very latest vehicles. So I'm now going to move all our stuff from London around through the Suez Canal and around to Beijing. So Beijing, this is a photo quite near the Olympic Park in Beijing. I think that's the Olympic Tower. And sort of most people's idea of what Beijing air pollution is like is when it goes like that, just a few days apart. And it's, again, very much in the public consciousness in Beijing. It's in UK newspapers, but also in international news, and right through the different types of newspapers. But also, in case you weren't that bothered about air pollution, there's a bar in Beijing that reduces its prices of beer when the air quality index is over 200. So there's some research that says it makes people sad and depressed when the air's more polluted. So this bar's decided that they'll make their beer cheaper, I guess, to try and offset that. So anyway, we had a project. It was partly funded by, or jointly funded by, the UK Environmental and Medical Research Council and the National Science Funding Council of China, and partly the Newton Fund as well. Around about £12 million, jointly funded from the two countries, 30 institutions, about 180 participants. I estimate around about 200 instruments involved. The project actually, or the programme actually involved 5 different projects. So we had a project looking at emissions, we then had a project looking at processes and how these emissions get processed, a couple of projects looking at the health effects and personal exposure, and then a project looking at solutions and basically taking the data from the emissions and the processes and the health and looking at what actually the Chinese authorities could do. So it was a joined up programme, but with 6 individual projects within it. But what I was involved in was the emissions and the processes part, and that were based around 2 field sites. This is Beijing. You can see the airport here. I think the Forbidden City is somewhere down here. The Institute of Atmospheric Physics site here, which was our main sort of urban site, and also a site in a place called Pinggu, which was what we classed as a rural site. Zooming in on the Institute of Atmospheric Physics site, these are the sort of ring roads that now sort of surround Beijing. I think there's 6 or 7 of them. The IAP site is just here, so just in between the 3rd and 4th ring roads. And it's based around this very spectacular 350-metre meteorological tower. This was actually built when this area was all countryside in the 60s, but it's sort of been enveloped by the city and has managed to survive not being torn down. But it's a fantastic facility we can use to do we could use to do a lot of good science. And this is a picture of our walk to work every day from our hotel along this sort of canal in summer and in winter. We shipped out 3 shipping containers from the UK full of equipment and used another couple of local shipping containers. This is a photo looking down from 100 metres on the tower. These were the instruments to measure the sort of processes, and we had a flux container as well where we ran a sample line down the tower from about 100 metres in order so that we could do the eddy covariance measurements. This is just the list of the measurements we made. I won't dwell on this too much, but like I said, we think we covered pretty much everything that we needed to cover. We had things like a time of flight SIMS instrument that was able to basically measure most things, but things like VOCs up to sort of C13 chain VOCs, and this will become important when I talk about ozone in Beijing a little bit later. I want to start off by talking about the eddy covariance fluxes. We had a huge range of fluxes measured, again from the top of this tower. Just some nice photos here looking at overseeing Beijing, and you can see this tower is sort of, or at least where we were measuring, is above most of the buildings surrounding it. Just the basic sort of core flux measurements, and you can see here the sort of an updraft and a downdraft where you can see the CO2 and the temperature and the ammonia all rising when the wind is in a vertical direction. But I'm going to concentrate on NOx and carbon monoxide because that's what my group made measurements of. This is our winter campaign in November and December 2016. and a summer campaign in May and June 2017. You see we've got really reasonable coverage of NOx and CO fluxes. There's a gap here. That data will get filled in. There were some data logging problems, but we do have that data. So we've got a really nice data series of the fluxes of NOx and CO. But just for simplicity, we put this on as a diurnal average, and the lighter colours for NOx and CO are the summer, and the darker colours in winter. And you can see we've got increased NOx emissions in winter and largely increased CO emissions in winter. We put this down to sort of more domestic burning and cooking in winter. We're not entirely sure that the reason for the increased NOx emissions in winter may be something to do with the catalysts in the vehicles not working as well. But you can see the sort of traditional diurnal cycle. This is local time where the traffic starts. But actually, what you might see in somewhere like London is you might get two peaks, a sort of morning and an evening rush hour. You don't really get that in Beijing. The traffic starts and then remains pretty constant during the day, and that's what we see in the NOx emission. I've plotted these up, or my student has plotted these up on these sort of wind donut things. These are you've got winter and summer NOx and CO. Again, the hotter colours are higher emissions, and this is the diurnal cycle, so you go from midnight to midnight across the graph here, and then this is obviously wind direction. And what you can see in both winter and summer for NOx and for CO is the higher concentrations in this sort of easterly, when the wind is from the easterly direction. And we put this down to, we're pretty close to this. This is the Trans-Tibetan Highway that comes in to Beijing. It's a really very busy road. And so we're hoping to be able to use that data to sort of try and pare down exactly where the emissions are coming from, because when the air's coming from that way, it'll be largely traffic dominated, just because of this. It's a sort of 5-lane each direction highway. But obviously one of the things we wanted to do was to assess emission inventories, and we had to calculate a footprint. You can see this is the tower and this is the typical footprint, around about 3 kilometres from the tower in the direction of the wind. There is an emission inventory for China, the multi-resolution emission inventory for 2010. It's at 3 kilometre resolution, and you can see IAP sits sort of somewhere between these 4 3 kilometre grid squares in the inventory. And this is sort of zoomed in on a Google Earth map, and that's an example of a footprint. So essentially, depending on the wind direction, we're measuring in 1 emission inventory square. And so if we do a comparison in that square, we see actually it's not too bad, particularly for NOx. And if you average it out over the day, the measurement and the estimate from the inventory are very similar, within error. You'll note that I said that this was a 2010 emission inventory. It's actually thought that the NOx emissions in 2010 are reasonably relevant to what they are in 2017. They peaked, I think, in Beijing in around about 2013, and then have started to come down again. So we're quite happy with comparing to a 2010 emission inventory. And again, just for a bit of fun, I put a comparison between the diurnal cycle of NOx in Beijing and London. Obviously, this is very sort of hand-wavy because of they're obviously in different sites. But what you can see, at least for those 2 sites, that London has emissions of NOx that are a factor of 3 or 4 more than Beijing for that site, for the BT Tower site compared to our IAP site. And again, that's largely due to the prevalence of diesel vehicles in London. Beijing essentially doesn't even allow trucks in during the day. They are only allowed in after midnight, or between midnight and 4 a.m. So that's where we are for NOx. But the last bit of the talk, I want to talk about ozone. So again, like PM, NOx, CO, SO2, essentially all decreasing, although, like I said, NOx peaked in 2013, it has started to decrease again. But ozone, measured in 12 stations around Beijing, is increasing. So there's been a 40% rise from 2004 to 2015, but also importantly an increase in the frequency of days above 60 ppb, one of the sort of health standards. So one of the things of this campaign was to try and understand what's going on with ozone, and more to try and give some advice as to how best to control ozone. Again, this is becoming the public consciousness in Beijing, ozone overtaking PM2.5 as the top pollutant, obviously in summer, across different media outlets in Beijing. It's not just a Beijing problem. There was a recent report on ozone worldwide. These are quite complicated plots, but the arrows essentially, when they're red and in an upward direction, show increased ozone. And in Southeast Asia, around Southeast Asia, ozone is increasing. It has started to increase in certain US and European cities as well. So here's our time series from summer for our campaign. The one to concentrate on is ozone here, obviously, in the purple, and you can see we get these events where ozone builds up, and this was the most, the highest one, where we reached about 190 parts per billion of ozone, but also had another event later in the campaign. You can see the temperatures here ranging between sort of 25 and close to 40 degrees on some days. And then just for example, concentrations of CO, benzene, SO2 and isoprene, which could be an important driver as well. Just to contrast it with winter, now these are on the same scale. You can see obviously temperatures have dropped, radiation has dropped, NOx is massively increased, ozone can hardly see on the scale, and the concentrations of CO, benzene and SO2 have increased. I gave a talk in Beijing at the end of our campaign, a thing they call Science on Tap, which was a public sort of outreach talk, and I thought, well, let's put on London at the same time. So I picked a similar site in London, an urban background site, and plotted the NOx at the same time that we were there. And you can see, at least for large parts of the time, the NOx concentrations are pretty similar between Beijing and London. Remember I said NOx emissions in London were higher, but then the meteorology in London is such that it actually keeps the concentrations lower than they otherwise might be. But if you plot ozone, obviously Beijing's significantly higher ozone. London almost never breaks the health exposure limit, whereas Beijing does on around about 50% of the time. And if you put carbon monoxide in there, again, London almost don't bother to measure carbon monoxide anymore because it falls off the bottom of the scale of the instruments, but our measurements of CO in Beijing show that there is still significant CO, up to a couple of parts per million at times. So this is ozone across those 12 sites for our campaign period, and you can't really see, but what I want you to take away from this is that essentially ozone at all of these sites is virtually the same. This is a correlation plot, and the thinner and the redder the sort of ellipse there, the better the correlation between the two sites. And you can see for all of the sites there, ozone is pretty much the same. So we can think of Beijing kind of as a big homogeneous chemical reactor where at least for ozone, the concentrations are very similar across the city. If we look at the air mass origin of ozone, these are 24-hour high-split back trajectories coloured by ozone measured at the site. So these are where the air's come from, measured at, arriving at our site, and you can see almost all the high ozone days is when the air comes from the south. And south of Beijing is essentially where they've moved the power generation and the industry to, largely before the Olympics. There aren't any coal-fired power stations in Beijing anymore, but there are in these cities to the south. So what that's done is, in terms of ozone, it picks up those emissions and transports them, and then the processing happens, and so Beijing is starting to get more ozone issues. And you can see that if you look at our wind direction plots, coloured by CO and SO2. When you get air from the southeast, the CO is highest. From the southwest, the SO2 is highest. And actually, the emission inventories for CO are very good in Beijing. So what I thought I'd do is plot ozone against NOx for our winter and summer campaign. And you can see a sort of traditional thing that you might expect in winter, where you get low ozone at the higher NOx. This is just for daylight data, but then in summer you've got virtually no correlation between NOx and ozone. So these higher ozone periods, basically the NOx is not changed as we go up here. So then what we wanted to do is put some other cities on there, just to have a look. So this is London in summer from that period, and it sits around there. And if you take data from Los Angeles, from the COWNEX campaign in 2011, I think it was, it sits around here. So you see Beijing's significantly higher. I really want to add Mexico City to this plot as well. That would be really good. So it will ruin my title. But if we then look at an ozone isopleth, so where the three cities sit, you can see London here, London here, Beijing here, and sorry, those are different colours. This is Beijing, this is Los Angeles, and this is London. Apologies, they're the wrong colour. And you see Beijing has got higher ozone, but it's also lower down the NOx axis, but higher up the VOC axis. And this was very basic work, but what we wanted to do was then put all of the chemistry measurements that we made and to try and improve this isopleth for Beijing. So it's a modern low NOx cities, but with CO and VOC similar to the 1980s. So this is an odd combination that may not have been seen before. I just thought I'd add, we've just finished a campaign in Delhi, and I just thought I'd add that to it. So you can see Delhi actually, if we take that off, it's got higher ozone and higher NOx. So probably Delhi's sat somewhere here, and we intend to do this type of analysis with Delhi over the next sort of year or so. Apologies for the change of background, but I couldn't make this plot fit my white background because of these white points. What we wanted to then do is compare VOCs between London and Beijing. Now these are normalised, so it's not that the actual levels of VOCs are higher in Beijing than in London, which is no surprise, but the mixture appears pretty similar. So, and this is the classical VOCs, 32 VOCs that you get from a standard GC, C2 to C7 non-methane hydrocarbons, and C2 up to C2 benzenes. If you compare London and Beijing, they all sit on this line. And that's been seen before, not in papers that have looked at ozone, but in papers that have looked at SOA in Beijing, which has been largely what a lot of research has concentrated on. But we have these measurements from the two-dimensional GC of higher molecular weight VOCs, and you can see here these are the straight-chain aliphatics, so greater than C8, and you can see London has significantly higher concentrations of those, which is from the diesel fleet, but Beijing has higher concentrations of these C3 substituted aromatic compounds that London doesn't have. So the mixture then, once you add in these measurements from the two-dimensional GC, the mixture starts to look very different between London and Beijing. You can't really see these plots very well, but this is total VOC reactivity with OH in London and Beijing. London, it's around about a second to the -1, largely dominated, like I said, by these unsaturated aromatics, unsaturated VOCs, aliphatics. They are there in Beijing, but these aromatic compounds now take up this large part of the pie, and the total reactivity is a factor of 5 higher. What about other cities? It's quite difficult to directly compare because previous slide was York data versus York data, and we've tried to pull this out, then York data versus LA data from a completely different instrument. But again, if you look at London and Los Angeles, actually the mixture appears fairly similar. So it looks like Beijing is particularly strange with these large aromatic compounds. Oops. And again, just some very early data from Delhi, and we've got ethane, ethene, ethyl benzene and benzene, and you can see it looks actually like Delhi, as we suspected, has got higher VOCs, at least for these three, and possibly not for the substituted aromatics. So this is going to be then a really interesting study to when we come to look at the Delhi data and compared to the other cities. So what have we done with this data? So we've set up a model based on the master chemical mechanism, which I won't go into in any detail, but is basically a near explicit chemical mechanism that looks at the breakdown of VOCs with OH and ozone and NO3 and can look at their ozone forming potential. We run this for a 6-day period, and we constrained it to the measurements of all of our VOCs. And what we have showed is it shows some skill at predicting ozone. We're not trying to predict ozone so much, we're using it for sensitivity, which I'll come on to in a minute, but essentially we can get ozone almost right, and also formaldehyde as another tracer of chemical activity we can get reasonably right once we tweak the model enough, but it's constrained by the measurements of VOCs and the measurements of emissions of NOx. So then we want to use this to show the sensitivity of ozone to various VOCs. Now I'll try and talk you through this. Essentially, this is where we are now. So this is a multiplier of 1. This is where we are at the moment. And then what we've done with the model is to either increase all these different compounds, each individually, or decrease them and see what happens to ozone along here. And essentially what you can see from this, and that's this line here, is the aromatics compounds would by far outweigh any other reduction. So if you reduce aromatics by 50%, you would have 0.6 or 60% of the ozone remaining. So it's by far the most important lever, if you like, to reducing ozone, is these aromatic compounds. The dots along here are if we put this, if we do this work with the GeosChem global chemistry model, which doesn't really have an aromatic scheme, so that actually you don't pick that up if you do it with a regional chemistry model. So yeah, that's really the key take-home message from this. The other one actually is that if you were to reduce NOx, you would increase ozone still. It's still at a point where reductions in NOx without reductions in the VOCs would make ozone worse. So if we want to unpick and this is kind of zoomed in a bit closer, again, of the individual aromatics, these are the large aromatics, and this is anthropogenics. Again, you can see that it's the large aromatics and the anthropogenic compounds that are the ones that you want to reduce. If we put this onto an updated isopleth, this is where it sits. So again, there's the Beijing authorities really need to prioritise VOC reductions to give you the most benefit in reducing ozone. So if you reduce VOCs, you're going to come down here. If you reduce NOx, you're not going to reduce it as much, or at least initially you're going to increase it. But there is a risk that these, as I said before, these NOx reductions are going to outpace the VOC reductions, given forecasts and the policy emphasis of Beijing. One thing that's initially came out of this, that these modelling inclusions we found were very sensitive to HONO. I haven't got a slide on this, but so nitrous acid. HONO there's significant daytime concentrations of HONO measured in Beijing, up to about a ppb, and there are various debates as to where this comes from, but one of the things is that it's a ground source of HONO. Obviously HONO is important because if it's there, it's going to break up and it's going to give you NO, it's also going to give you OH, so it's going to really speed up the chemistry. So if you just include the HONO measurements from the ground, which is where all our other measurements come from, actually your model can be really sensitive to HONO. But there is some data now that shows that the vertical profile of HONO, it drops off very quickly as you go up towards sort of 200 meters. So somehow we're going to need to put into the model a sort of average HONO across the boundary layer. And it's just a warning that if you're doing this work on a field campaign, it may appear that HONO is a very sensitive thing for ozone. But it's only the case if you take your surface measurements, which may not be particularly relevant to the entire lower atmosphere. Like I mentioned before, we've done some GeosChem simulations, and if we then put in a new scheme for higher aromatic chemistry, we actually get good reproduction of the daily VOC cycles and a reasonable reproduction of ozone. This shows the average ozone concentration across the whole of China, and this shows predicted change in ozone concentrations over the next 5 years, given that there could be a 20% NOx reduction, which is what the policy aims of the Chinese government is. And you can see that there could be a change of ozone of 4 to 6 ppb if the VOCs are not controlled as well. just finally, we also wanted to look at where these aromatic compounds are coming from. If we want to control them, we need to know where they're from. Again, you can't really see this slide very clearly, but we think it's in the content of gasoline. We think the content of Chinese gasoline includes these large aromatics for some reason, and that so potentially it's a reasonably easy thing to do to not have this in anymore. It would depend exactly which aromatics are in, and we're trying to do some work at the moment to actually take samples of Chinese gasoline, but we know that it is much higher than Europe and the US. And these C3 to C6 aromatics will make more ozone than the sort of standard toluene and xylene in gasoline. So just a few working conclusions on Beijing. We know that PM is on a downward trend. Also interesting, the implication of an upward ozone is if PM continues to drop, it will have an effect on radical chemistry. So at the moment, HO2, the key radical buffers, is uptaken onto particulate matter. Actually, if particulates continue to decrease, this uptake of HO2 may get less as well, or will get less as well, which is going to give you more radicals and hence more chemistry and potentially more ozone. These multiple studies have shown growth in Asian urban and regional ozone. We think it's down to this unusual urban mixture of high VOCs and sort of moderate NOx, and much higher amounts of higher monoaromatics, and in particular the large aromatics. So we are doing work at the moment to simulate the changes of VOCs with models like the GeoSchem. And the key thing is the high possibility that NOx reductions outpacing VOC reductions and making ozone worse. That's everything I've got to say. There's an enormous number of people that have done work into this. This is just a sort of a few of them from my group, Freya and Will, who are my PhD students, Jackie, who's an academic who provided the 2D GC measurements, and Rachel, her postdoc, Jim, who provided the VOC measurements, Andrew, Rickard and Pete, who essentially did the MCM modelling. You could probably tell I've not actually done very much on this work, and Ali Lewis, our kind of group leader, and the radical chemistry from a group in Leeds. But the whole project, in particular the Chinese project, involved an enormous number of people. That's from the UK side, that's from the Chinese side, so I'm not going to go through all of those. But yeah, it was a really major piece of work. We've got about a year left on the project, and hopefully it's going to produce some really nice results. And thank you very much for your attention.
Thank you very much, James. ¿Tienen preguntas o algún comentario? Ok, ¿me oyen? ¿Preguntas, comentarios? No? Not for a moment.
Thank you very much for your talk. Very interesting. We have also similar problems in Mexico. When we try to control the traffic, when we have high ozone, also we have been seeing that the ozone doesn't go down, and it's this thing of chemistry you're referring to. It will be interesting to see also this. Say if we have the same problems in Mexico. And just another one detail, did you pair measurements of emissions with your FTIR that you used on the road with with PEMS? You showed a graph where you have in the road. Have you paired with PEMS?
We haven't, no. Well, actually some work has been done on that. We haven't looked at the data yet. So some of the work in London did include some PAMS vehicles with PAMS included on them, but we haven't looked at that data yet. So there is data there from that. But
just to compare it to see if the measurements you're doing
yes
are related to PEMS.
Exactly. Okay. Yeah.
Hi, thank you for the talk, very interesting. I just wanted to get your feeling for the comment you made about ozone increasing in quite a few cities. and what it can be related to. I mean, on the other hand, PM is going down in many of the cities, so there would be less scattering
Yep.
of radiation. Has that anything to do with
So
ozone increase?
we think that, so there is a group looking at this in Beijing, and we think that it will have an effect, the reduction in PM and therefore the increase in light, but it's actually outweighed by the radical effect of reducing particulate. So the increase in radicals that you're likely to get because HO2 is not uptaken onto PM as much vastly outweighs the effect of radiation. Because obviously ozone is mainly a summer pollutant in Beijing, in most places, and the PM scattering is not as high in summer as it is in winter. It may have an effect on wintertime ozone, and there's some work, a group from Peking University looking at wintertime ozone and reductions in PM, whether that's going to start to make wintertime ozone an issue. But in the summer, we don't think that the scattering issue is a big one. It's outweighed by the radical chemistry effect of particles.
Okay. ¿Alguna otra pregunta?
Well, just a very silly one. You say C3 to C6 aromatics. Do you mean benzene with what does it mean, the C3 to C6?
It means 6 carbons on a benzene.
On the ring.
Yeah, yeah.
Okay. ¿Alguna otra pregunta? ¿No?
You mentioned the VOCs as Greece as well, but I saw that the isoprene, it's the second one. It's following. What happens in the isoprenes in the measurements? It means that Beijing is highest, and Delhi as well is highest the isoprene. So it means that the biogenics is.
Biogenics is still important, obviously, and could well get more important in future. We didn't so much look at the sensitivity of isoprene because there's not much we can do about it. This was a sort of policy-related thing, but from the top of my head, isoprene makes up around 20% of the OH reactivity in Beijing, probably a bit more in Delhi, but it's isoprene plus monoterpene, so all biogenics make up 20%-ish of the primary OH reactivity.
Okay. The second last one.
Yeah.
Sorry, I forgot to ask the second one. Your OX to your ozone against NOx. Are they all day measurements or are they just mid of the day?
They are daylight hours.
Daylight, all daylight hours.
All daylight hours, yes.
One last. No. ¿Alguna pregunta o comentario? No. Because I have one comment. Here in Mexico City, obviously, we are in the VOCs regime, but we have a second little problem that we have from new gasolines from the black market.
Mm-hmm.
So I don't know if it is those kind of fuel compounds are going to mix and increase the CO.
Yeah.
The ozone and the other precursors.
Very potentially, and it's obviously hard to know what's in them. Yeah, maybe, yeah.
Okay. ¿Alguna pregunta? ¿No? Bueno, creo que eso es todo. Vamos a dar una pausa.